Quality Control and Improvement, Module 3, Lecture 3. The learning objectives for Lecture 3 are to explain the statistical basis of the SHU-ACT control chart, including choice of sample size, control limits, and sampling interval. We'll also analyze the control chart to determine an out-of-control process. Reading assignment is Chapter 5, pages 175 to 217. So SPC, which is referred to as statistical process control, can be applied to any process. Has 7 major tools. The first and primary importance is what's known as the control chart. Then there's the histogram, the check sheet, Pareto chart, the cause and effect diagram, defect concentration diagram, and scatter diagram. Now, any given problem, we may not use all of these. And some of these are sort of redundant. You could use a check sheet, a Pareto chart. I rarely use a defect concentration chart or a scatter diagram, but they can be used, and in certain situations, they're very, very reliable. One fact in manufacturing is that no two objects are ever made exactly alike. It's impossible. The causes of variation can be subdivided into 2 groups. One is what's known as common cause variations, and the second is what's known as assignable cause variations. We'll take a look at each one of these separately. Common cause variations are random changes in the process that cannot be avoided. These small differences are due to the inherent variation present in all processes that consistently affect the process and its performance day after day after day. Variation of this type is only removable by making a change in the existing process. So in other words, you have to improve the actual process itself by using either different methods or better instrumentation, better instruments, better presses, whatever the actual manufacturing process involves. So this usually takes some kind of effort and time and money to fix. On the other hand, assignable cause variations can be identified as having a specific cause. Assignable causes are causes that are not part of the process on a regular basis. This variation arises because of what's known as specific circumstances. It is these circumstances that the quality assurance analyst seeks to find. So in other words, this may occur because, let's say, for example, you have one operator on a specific piece of machinery, and you hire somebody else, and he takes over. And you find doing your quality analysis that something's changed. Well, it's one cause may be is the new operator needs more training. So we can, if we find that out, we can assign that variation. It's an assignable cause. We know what caused it. It's just not random. It's specifically tied to something we can identify. A process that's operating in the presence of assignable causes is said to be out of control, an out of control process. And this is what we're trying to fix. We're trying to bring these processes into control such that there are only random variations in them. And we don't have assignable causes. So take a look at these 2 charts here. This is 2 normal distributions. They're both centered about mu here. What's the difference between the 2? Well, they have the same mean, but they have different variances. So see how the one with a variance that's smaller is much more peaked, while the one that has a bigger variance is much more spread out. Now, obviously, if we were manufacturing a process, which would we prefer? We would prefer the one that has the smaller variance, because our products are manufactured to a lot higher tolerance. Take a look at these. Here's another example where you have 3 distributions that have the same standard deviation, but with different means. This can also be a problem, right? Because if we're trying to center a process around 0, this one has a mean of over at 20, and this one has a mean of -10. Neither one of those are going to work. Those would be maybe out of spec, right? So it's what's important to keep in mind in these last 2 slides is that it's not only the variance that matters, it's also the mean that matters. This is better seen by looking at the following graphic. So let's say we have a manufacturing process where we're manufacturing dumbbells, for example. And these dumbbells have a certain specification for the weight. And so we're producing 1,000 dumbbells a day. And we set up a regimen where every hour on the hour, we sample a set of 10 dumbbells, pull them off the production line, and weigh each one, calculate the mean and the standard deviation. Then what we do is we make this time chart. So for example, time 0 is here, time T1, maybe that's the first hour. Time T2, that's the second hour where we take our second samples. Time 3, that's the third hour, etc. So time is flowing in this diagram from left to right, kind of into the board here. So mu0, that's our specification. That's our mean value, where we expect it to fall, the weight we want. We have a lower specification limit and an upper specification limit. Again, those were set at typically at plus or minus 3 sigma of our variance. So, up until time, we take our first sample here, everything's looking great. Both the mean and standard deviation are within their normal control values. You may look at it and say, okay, well, yeah, but there is some variation. Yeah, that's what's called common variation. Remember, no two products are going to be manufactured exactly alike. There's going to be subtle differences, even in the weight. If you weigh down to a fine enough scale, even dumbbells will have a slight variance. Now, what happens here at T1? Look, so T1 is this process here. If you look, what happens is we have an assignable cause occurs, and the effect is to shift the mean to a new mean. So here, the mean jumps up to mu1 here, and at this point, this process is out of control. And so it continues on. Time T2 here, we take another sample. And what happens now is the mean shifts back to its regular value, but now the standard deviation expands, and this is the result of another assignable cause variation. Time T3, we're over here at T3. There's another assignable cause resulting in both the mean and, in this case, the standard deviation shifting the other way. So from time period 1 to time period 3, you've had several assignable causes variations, and this production has been out of control. So part of what we're trying to do here is understand how this process occurs and be able to remove these assignable causes and get this process back under control. So control charts are really going to help with this process. These are graphs that plot your process data in time-ordered sequence. So instead of the complicated graph I showed before, we lay this out on a kind of a horizontal vertical graph. They're not three-dimensional. So these kind of control charts indicate when your process is out of control and helps you identify the presence of these special calls, or what's called assignable cause variations. Most control charts include a center line. Now this center line typically is going to be about our sample quality characteristics. So this could be the mean, for example. It could represent the sample variance. It's whatever we choose to plot here. Now, the upper control limit and the lower control limit, when we plot these in Minitab, Minitab will produce these lower and upper control limits at plus or minus 3 sigma. We'll enter our data in the Minitab, and we'll select the control chart option. Minitab will just plot all these dots, hook the dots up by a line segment, and it'll produce the values for the lower and upper control limit. So what's the significance of the control chart, and how does it relate back to the last module that we did on hypothesis testing? Well, the big deal is, as we're plotting here, a point that plots within the control limits, between the upper control limit and the lower control limit, indicates the the process is in control. For example, so if this was the mean, the green represents the mean, then that would show that no action is necessary. They plot within in the bands. A point that plots outside of the control limits, for example, the points in red here, indicate that the process is out of control. That would mean the mean does not equal the sample mean. This is where we have to take corrective action to find and eliminate these assignable causes. So, for example, in this particular one, this was taken from this chart displays the length of manufactured camshafts over time. The 2 points above the upper control limit, shown here in red, these are out of control points and indicate the camshaft and these sample groups are a little bit longer than expected. So there's a close connection between the control charts and hypothesis testing. The control chart is a test of the hypothesis that the process is in a state of statistical control. A point plotting within the control limits is equivalent to failing to reject the hypothesis of a statistical control. And a point plotting outside the control limits is equivalent to rejecting the hypothesis of a statistical control. So this lays the theoretical framework for why the control chart is useful and why we can use it. So for illustrative purposes, let's look at a specific example. Let's say we have a population of individual measurements, X. And so X here again could be a length of a board, a weight of a dumbbell, whatever our manufacturing process is producing. Let's say we have a whatever our measurements are from the population, we know that the normal, it's normal, have a normal distribution with mean of 1.5 and variance of 0.15. Now, here, I didn't put units on this. This could be pounds, it could be inches, it could be feet, whatever our units are. Now let's take a sample of this. So we're manufacturing. Let's say we're manufacturing 1,000 dumbbells a day, and you know, our population has a mean of 1.5 pounds and a variance of 0.15 pounds. Let's say. And every hour on the hour, we take 5 dumbbells off the production line, and we weigh them, we measure them, and we determine that the sample mean is 1.5, and the sample variance is 0.0671. How do we get this value? Well, remember, if we know what the variance of the population is, 0.15. We can divide by the square root of n, which is the number of samples. So that's 0.0671. That's where we get the sample variance. Now to actually construct the control charts, the center line obviously is at is at the mean, 1.5. The upper control limit and lower control limit are set at plus or minus 3 sigma. So I've done the calculation for you here that, you know, it's 1.5, that's the mean, plus 3 times sigma, with sigma we calculated. So what I'm saying is, you know, the significance of this is that this control chart is exactly equivalent to testing this hypothesis. The null hypothesis is the mean is 1.5, and the alternate says it's not. So, you know, instead of doing that complicated, you know, one sample Z stuff, we can just look at the control chart. Minitab will graph the control charts for us. We can look and see if we fall outside or below the control limits. So it's a much more graphical, visual way to do statistical analysis is by using the control chart. That's why it's so popular. So what's the general model for control charts? Let's let W be the sample statistic that measures some quality characteristic of interest. And suppose the mean of W is mu W. So W here could be the weight, the length, whatever we want. And the standard deviation of W is sigma W. Then the center line, upper control limit, and lower control limit are plotted by using this example here. L is the distance of the control limits from the center line expressed in standard deviation units. So typically L here is 3, plus or minus 3 sigma is what we typically use. The center line is going to fall right at the mean of whatever we're measuring. So how do we improve using control charts? Well, the thing we do is, we have let's say we have raw materials being fed into our manufacturing process that's producing an output from our factory, whatever we're manufacturing. We take samples from the input, from the population, and we send them to our measurement system, and we measure, we weigh whatever we need to do to measure what characteristic we're interested in keeping under control. If we detect assignable causes, we identify the root cause of the problem, we correct it, verify and follow up, and then we keep measuring. So this is a continual kind of process, 24/7. Is we're always measuring, we're plotting on the control chart, we're trying to detect these assignable causes and correct them, and then so we can keep our process under control. One issue you might think about is control charts is, you have to specify both the sample size and the frequency of sampling. Again, if you're running your manufacturing plant, how often are you going to sample? How big a sample are you going to draw? Obviously, it'd be good to draw as large a sample as you can, but the problem with that is if your sample size is too big, you can disrupt your manufacturing process, and that's no good. It can also be very costly to do that. So, there's a lot of factors that have to be considered here, definitely, you don't want the process to operate out of control, because that's very, very non-productive as well, and you don't want to be putting out faulty products. So there's a lot of things to balance here, and a lot of it depends on the specific manufacturing process we're trying to control. Another thing you can have with control charts is you can have patterns that show up on control charts, and these may indicate an out of control condition when more and more points fall beyond the control limits, or when the plotted points exhibit some kind of non-random pattern of behavior. So even if all the dots are plotting within the control band between the lower control limit and the upper control limit, you can notice patterns there that you want to take advantage of to try to reduce the variability of the process. Typically, we define what's called a run as a sequence of observations of the same type. So, for example, if you have 8 dots in a row that plot above the center line, that's often taken as a signal of an out of control process. So if you have 8 dots in a row above the center line, or 8 dots in the below, 8 consecutive dots above or below, that indicates that a process is out of control as well. So in each manufacturing process, the quality control supervisor is going to determine the exact thing that he wants to monitor and what he considers to be out of control in conditions. So here's an example here. So we got a manufacturing process that's we're measuring something here, that this is our center line is our mean, and we have sample numbers. So these sample numbers are taken at regular intervals. This could be every hour. We could have every hour we draw so many samples, and we measure, and we calculate the mean. Let's say we draw 5 samples at hour 1. We measure the length of the object, and we find the mean, and we plot it. And hour 2 we do exactly the same thing. So what pattern you kind of notice here? Well look, you got some patterns that are falling in here. Look at the dots from like 4 to 9 here. They don't look exactly random, do they? I mean, if it was exactly random, this thing would be bouncing all over the place. But this indicates kind of a pattern here. This is what's called a run. So you got several dots here plotting in the same fashion. Also, you got another one here. These are kind of falling, and also here's a big run. So you're going to have some of these, but a run of length 8 or more is often taken as an out of control condition. So here you got 1, 2, 3, 4, 5, 6. It's kind of close. If you had a couple more there, even if it didn't exceed the upper control limit, a lot of supervisors would take that to be an out of control condition, and you would start looking and investigating to see if there's some assignable cause here. This is another one that looks kind of suspicious. I mean, look, you almost got a kind of sine wave going on here. This was like cyclical kind of behavior. Uh, they all fall within the upper control limit and lower control limit, but this cyclical nature, again, is not random. So, you need to investigate to figure out what's going on here. Some problems that I've shown here, it could be operator fatigue. The operator gets tired. Maybe needs a break. You know what I mean? It could be difference in materials, heat buildup or stress. There's all kinds of things that can cause this. But the key thing is, if you see this on your control chart, you need to start investigating what's going on. Even though the process is in control theoretically, it can quickly become out of control because something's going on. This is a non-random behavior. So, elimination of these patterns, these cyclical patterns, or these runs, will result in an improved process. It reduces the variability within the cyclic pattern, and so it makes the variance much more tighter. So which one of these would you, if you were manufacturing product, which would you prefer to have, A or B here? This one's, you got some problems here, right? Falling out, you're manufacturing products here that are outside of the spec line, so obviously that's a problem. You want this, theoretically, you'd want it to be very as centered as possible, and the variance to be very, very tight here, right? You want some room for error here, right? So if the process shifts just a little bit, you'll still be within control here. So ideally, you want this very narrow. There's a lot of, again, there's a lot of theories on what's the best way to go here, and it depends on what book you look at. One kind of standard book is from Western Electric Statistical Control Manual back in 1956, which again is over 50 years ago, but still has some very good stuff in it. It suggests that process is out of control if you have any one of these conditions. If 1 point plots outside the 3 sigma control limits, if 2 out of 3 consecutive points plot beyond the 2 sigma warning limits. So a lot of people, they'll plot the upper and lower control limits at 3 sigma, but they'll also come in at 2 sigma and they'll plot what's called warning limits. And it does kind of clutter up your chart, but it can give you kind of a early indication if something's going wrong. If a dot points at 2 sigma, you don't got much longer before it gets up to that 3 sigma line. Another point that the Western Electric book had was that 4 out of 5 consecutive points plot at 1 sigma or beyond from the center line. That's another indication. If 8 consecutive points plot on one side of the center line, this is kind of run stuff here that we talked about. But in general, your supervisor, or if you're the supervisor, you're going to, depending on your manufacturing process, you'll hone this down and to figure out exactly what works for you. Obviously, if a point plots outside of the plus or minus 3 sigma, well then that's obviously out of control. But there may be other cases where you want to kind of take a look and see if you can tighten things up a little bit. Okay, so let's move on here. So one thing you have here is phase 1 and phase 2 control charts. Standard control uses involves 2 distinct phases. Phase 1, typically you're initially setting up your procedure. You're plotting your dots. You're trying to figure out if this process is in control at all. Once you get it in control, by eliminating those assignable cause variations, then when you get new data in, then you can sort of compare it with something you already have there. So the phase 2, that's what's called phase 2 here. You have a clean set of process data gathered under stable conditions. Phase 2, you're just using the control chart to monitor the process. To make sure that it doesn't go out of control. During phase 1, you're just trying to literally get it in control. Initial setup kind of thing. So a lot of reasons for the populated control charts. Again, they're a lot easier to use than hypothesis testing and statistical methods. They're very, very proven. They've been used for 50, 60 years. Very good for diagnostic information. They provide a lot of information about process capability, which we'll talk about in a couple of modules down the road. Uh, so, you know, much of our focus going forward here is going to be on control charts. There's two basic types of control charts. There's control charts that deals with what's known as continuous data. That's our variable control charts. Then there's control charts that deal with attribute data. Those are usually discrete data. And moving forward here, this is the biggest, part of the course is, the next three modules are going to be primarily dealing with control charts and how to analyze them and how to use them. A lot of different demos. So I don't want to go in this chart too much here, but basically, if you got continuous data like feet, you're measuring something, a length, a weight. That's a one type of control chart. The other type of control chart is like discrete data, like yes or no, is good or bad kind of thing. And so we'll look at all these kind of control charts down the road, but this is just kind of a general overview of control charts here.